Can you guys see this the screen?
Yep, I can see it.
We'll give it a couple more minutes and then we'll start the introduction. Thank you all for joining us today. It's also National Aviation Day, so this is a perfect way to celebrate aviation of the past and also of the future and the present. All right. So quick, we're going to start with a Project Boom design review. I'm very excited to present a team of young engineers working to build a supersonic autonomous vehicle. So, hello, we have some of the upcoming events for AAIA. I am Aldo Martinez, the AAIA local memberships and awards chair. And we have some events coming up. August 22nd, we will have the Space Architecture Gathering. On the 29th of August, we will have a K-12 event. On September 5th, we will have an e-Townhall with Bill, an AAIA honorary fellow. September 12th, we're going to have an aerospace cybersecurity event. On September 19th, we will have the university CubeSat project and student presentation during COVID-19. September 26th, we will have Aquarius, a reusable water-based interplanetary human spaceflight transport. October 3rd, we will have Mission to Pluto, presented by Alice Brown. On October 10th, we will present Inventi, the Joint Strike Fighter. On October 24th, we will have Chemistry in Space with SCALASCS and AAIA LALV. For October 31st, we will be celebrating the ISS 20th anniversary. And for November 7th, we have the Perlin glider, and November 14th, Voyager 1 and 2, humanity's most distant explorers. So as you can see, we have a fall full of amazing events put on for the aerospace community of Los Angeles Vegas section. But during this time, we are open to anyone who is interested in participating in those events. You can definitely contact me or contact the LALV section chair or the website. So quick, I'm extremely sorry. I don't think I was sharing. So I'll leave the event out for a quick second, just for anyone who's interested. Again, just a quick brief suggestion, try to use the telephone feature. It allows you to have better and more constant connectivity. Also, understand that we are part of an industry that is that functions a lot with proprietary data. So when the questions come up or when you're able to communicate with the panelists, please be considerate that we might have people who are not ITAR compliant, or we have other nationalities, or please keep any trade secrets from your companies to yourself. We are not able to monitor who isn't in the cause to the level that we can secure any trade secrets from being let out. So a quick pitch for why join AAIA. So we are in Southern California. The aerospace community is very vibrant. We have the James Webb Space Telescope, which was built here in Redondo Beach. We also have some of the lines for the F-18 and the E-18. We have the Mars Insights, the operations being run off from Southern California, and we also have JPL building the other robotic explorers. We have a planetary defense, astro exploration, and space tourism is just around the corner from us. And of course, we have a lot of the rocket technologies being developed both in the undergrad, graduate, and professional levels. So if you're considering a career in aerospace or are interested to be more involved with the aerospace community, do consider AAIA as a professional society to join. We provide the latest technology updates and trends. We are great to produce events for networking opportunities and job leads. And this is the perfect way to become active in your field. And organize events like this one. I myself joined around 2 years ago and am excited to present events like this. Again, if you're a student and are interested to take on some leadership skills or leadership positions, AAIA Los Angeles Vega section definitely can help you build that resume and those skill sets as you transition into a professional level. And AAIA right now is the forefront for the aerospace community in the nation. We're shaping the future of aerospace. We have over 30,000 members, around 1,000 members in our local section. And we are headquartered in Renton, Virginia, but we stretch across the whole world. And we are often connecting members in between sections and in between countries. So a little bit more of the benefits of becoming a member. And there are 6 categories. Again, if you have any questions regarding the categories or how to join, what benefits we can provide, don't hesitate to reach out to the local chair or myself. We can give you more, walk you more through it. And if you want to have a somewhat of a trial run, we do offer any membership that is free for 1 year. And so you're able to take advantage of that right now and be able to be a member and take on the opportunities that AAA members have. So again, here is some of the contact information. I am the local chapter membership chair. The first name on Aldo Martinez, aldomore@usc.edu. Feel free to send any emails, any suggestions, comments, or questions you have. I'll be happy to answer them. And if you want a quick link for the 1 year free membership, go to AIAA.org and hit on e-member. All right. So for the Project Boom design team, I'm sorry. This thing logged in.
Are you ready for us to take over, Aldo?
Give me one quick second. All right, I have a couple more things, but there we go. All right, so a quick agenda of how it's going to go down today. We will be presenting Project Boom and give a quick brief intro of the team. I know they have more prepared and a lot of amazing facts and a lot of what the team buildup is. So we'll be looking forward to that. We also have the judges introduction. We were able to curate 5 amazing judges to help the team kind of develop itself and develop its pitch. And we'll be able to ask some questions, and they have a broad range of expertise ranging from tests to systems to avionics, and hopefully they can provide some input to a fast-paced environment that is Project Boom. After that, we'll let Project Boom do their presentation, and that will be followed by the judges' comments and questions and answers that they have for the team. And then around 5:20, we'll open it up to all the attendees to ask their questions, and we will be able to close out around 5:55. But we do have more time if needed, and if anyone is interested, we can definitely accommodate. So a quick teaser of what Project Boom is. It's an online student design team. They're adapting to current times. So all the team is spread out, not only across the country, but across the world. So we have students from many different countries, as long as from different education levels, from high school to undergrad to graduate degrees. They're trying to build a supersonic UAV. And the way that I found them was through a Reddit post, and that Reddit post made them really grow in size. And I know give a little brief on how they took that approach. So for the judges, we have first Noah Brooks, and I will let Noah Brooks give a quick introduction about himself. Hey, Noah.
Can you hear me?
Yes.
Hey, my name is Noah Brunk. I'm with Hermias. We're designing a Mach 5 hypersonic passenger plane using a combined cycle or turbine-based combined cycle engine. We've recently tested it between Mach 0 to Mach 4 using the turbine below Mach 3 and then using a ramjet above that. I went to Georgia Tech for undergrad and grad, and a couple memorable projects are below. Just notably, I think the one I'm most proud of was the first orbital landing and subsequent reflight of a booster that was at SpaceX. And I was responsible for designing a lot of the mechanisms and components to survive those environments. So looking forward to what you guys have. Yeah, I'm excited.
All right, thank you, Noah, for joining us. And we also have Dean. Hi, Dean. Can you introduce yourself?
Yeah, sorry, I just unmuted myself. Good afternoon, everyone. My name's Dean Cox. I'm actually living here in Seattle, Washington, but originally from the UK. Started my career at Airbus in the UK as a structures design engineer on the A321 airplane about 30 years ago. So I've been doing this for a long time. I've worked for major OEMs around the country, and being based in Seattle, I work for consultancy now, working mainly with Boeing, but do work with all OEMs around the world. Got my degree in engineering at the University West of England, and I've done many different things, including being a director at Airbus in Mobile for interiors for the A350, and lots of complicated systems for Crane Aerospace. One interesting thing about the supersonic project you guys are working on, my father is an aerospace engineer as well, and he actually worked on Concorde. Concorde was designed and built by French and UK companies, and my father was working for British Aerospace at the time, who was part of the Concorde team. So has some good knowledge on supersonic airplanes. I'm really looking forward to what you guys are going to talk about today. Thank you.
Thank you, Dean, and I mean, great kudos to your father for being part of the Concorde team.
Yeah.
And you have an amazing background. I'm sure that the team will enjoy a lot of your comments and your input that you have for aerospace engineering as a whole.
Sure, I'll be listening. Thanks.
And we also have Daniel. Hey, Daniel.
So yeah, I am Daniel Guevara. I'm currently working at SpaceX. I previously worked at Raytheon, and I know Aldo from grad school. We worked on the Hyperloop design team at USC. Since then, I've worked on the Europa Clipper, which will hopefully launch in the next few years. Various defensive missiles, particularly the SM-3 and the AIM-9X Sidewinder, and I'm currently working on the Starlink constellation.
Thank you. It's great to hear you again, Daniel. Back when we were in college, me and Daniel were in a similar team like Project Boom. So I'm glad that you can share a lot of your expertise that we've built up in the team to this brand new kind of design challenge that they're taking on.
Sure. Yeah. Thanks for having me. Excited for the presentation.
And we have also Jesus. I believe Jesus will be joining us very soon. We'll come back to him when we are ready for questions as well. For him to give a quick introduction about himself, but he's right now in Lockheed Martin, and he's worked for JPL doing the Mars 2020 systems test bed, and he's also done A-10 replacement, aircraft conceptual design, and before that, he worked at Lockheed Martin doing the Orion capsule retrieval mechanism. Hi, Kushbu, can you introduce yourself?
Hi, everyone. My name is Kushbu Patel, and I'm from Long Beach, California. I currently work at Relativity Space and as an avionics hardware in the loop engineer. Prior to working at Relativity Space, I used to work at Virgin Orbit And Virgin Orbit's also located in Long Beach. And my project was also hardware in the loop, but for an air launch rocket system. I went to University of Texas at Austin, and I graduated in May 2016. I have a Bachelor's of Science degree in aerospace engineering as well. A few projects, and like I mentioned, at Virgin and Relativity, I work on developing the hardware in the loop test system. At my current place, I also develop other test systems for qualification acceptance testing, as well as doing all the fairing separation tests and state separation tests. And in high school and college, I participated in various different organizations by NASA, as well as Elon's SpaceX Hyperloop competition. So have a few past experiences of flying in the Vomit Comet, which was incredible, as well as participating in a scholars program by being nominated by my state senator in Texas. So really excited to be here, really excited for the presentation, and looking forward to meeting the rest of the panelists and attendees.
And with that, we wrap up our judges' introduction. As you can hear from their amazing experiences and memorable projects, they have a lot of expertise and knowledge to offer to this team. And without further ado, I'll turn it over to Project Boom.
To go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
Project Boom is a big deal because nobody else is doing it.
Some would have us stay where we are a little longer, to rest, to wait. But this country of the United States was not built by those who waited and rested and wished to look behind them.
I was literally so excited that my heart rate rose up. That sort of kind of excitement is what I felt, and that's why I sort of joined to do this project.
If this capsule history of our progress teaches us anything, it is that man in his quest for knowledge and progress is determined and cannot be deterred.
When I walk, I've just kind of been picturing our aircraft and what it would be like, and just going blasting through this big valley that I get to kind of look at, And yeah, it's exciting and it carries with me and I can't hardly turn it off.
Hello, everyone. Thank you for joining us tonight for the first Project Boom Town Hall. First, I want to give a huge thank you to Aldo Martinez and AAIA for hosting us for this event and giving us a chance to tell our story. So today, we're going to introduce you to our project and give you an overview of our organization and how we market our project and how you guys, finally at the end, we'll allow you guys to answer some questions or ask some questions. To start, my name is Colin Watson. I'm currently a second-year aerospace engineering student at the University of Oklahoma. While at school, I actively participate in OU's FSAE design team, student government, and undergraduate research in our heat and transfer lab. However, more relevant to today's presentation, I am the founder and lead for Project Boom. We were founded in April of this year by myself and our chief engineer, Replogle, with the goal of being the first student group to design, build, and fly a supersonic RC aircraft. In the 4 short months since our inception, we have onboarded over 192 members with more than 70 different universities in 20 different countries around the globe. We are truly a one-of-a-kind global design team with membership including high schoolers, PhD students, and everyone in between. Tonight, we're going to give you a sneak peek at how our amazing team of students is working together to break records. This is not intended to be an in-depth design review, but rather an introduction to Project Boom. If you're interested in attending a more in-depth review, please reach out to me for more info. And if I could ask everyone to please hold all questions till the end, there will be a Q&A following the presentation. So when starting or joining any project, an important question to ask is why? Why am I going to dedicate a significant amount of time and energy to this team? For us at Project Boom, it's because we're not willing to stop when things get hard. In the past year, our world's been rocked by the COVID-19 pandemic. For many students, that has meant the loss of internships and the invaluable hands-on experience that they provide. Instead of sitting at home and fine-tuning our Fortnite skills, we got right to work creating our own engineering experience. Every member on our team realizes that there's no time to waste. We are passionate and driven towards becoming better engineers today so that we can solve the problems of tomorrow. So now you know why, but I'm sure you're wondering how. First, we started by organizing our talented leadership team, many of which you will meet later today in the presentation. Next, we set up a Slack channel for all internal communication among our team members. Since the channel's creation, our members have sent a whopping 30,000 messages amongst each other. And finally, we established key relationships with our amazing sponsors and advisors, something that has proved to be crucial to our success. So now that you know who we are and what we're trying to achieve, I want to introduce you to our chief engineer, Replogle, to talk about some of the more technical details of our project.
Yep. Hi, everyone. Thanks for listening in. So yeah, my name is Replogle. I recently graduated from Oklahoma State University, where I earned degrees in mechanical engineering and aerospace engineering. I'll be beginning a combined master's and PhD program this fall at the University of Cambridge in future propulsion and power. In general, I've been more of an engine sort of guy. I did some turboelectric propulsion research, and that was what my capstone was over at OSU. And then I do work full-time currently. I'm a intern at Southwest Research Institute in San Antonio, Texas, where I'm within the mechanical engineering division and the rotating machinery dynamics group. So when Colin came to me with this idea, it was around April. And, you know, he pitched this idea of a supersonic plane. And of course that got my interest. But the first thing I wanted to do was just sort of see how feasible and how difficult this was going to be for us. So I used, you know, the resources. I had an undergrad to do some sort of elementary analysis. You can see here on the left is just sort of a benchmark data graph of drag polars for some different like fighter aircraft. And on the right is kind of a crude modeling of that for what we could expect potentially for a small UAV. That orange line there is the required thrust. So that's really what this all came down to from the beginning, is can we get enough thrust? So I kind of scoured the internet, made a long spreadsheet of every engine that I could find. And no, there's not a commercially available option that can get us through the sound barrier. But I found initially, if we got an 85% increase in thrust, we could potentially do it. Obviously, there's a lot of assumptions that go into that number. But with all that being said, I decided, and Colin decided as well, that it was kind of close enough for it to be worth our time. And it's going to be a really interesting project to give it an attempt at. So yeah, kind of the next goal thing to do was set up our project goals, sort of the timeline, and what are the major milestones that we need to hit. So you can see on this next slide here, Colin and I sat down and did like a really preliminary Gantt chart. I think this was back in May. And some major things were to figure out what our aircraft drag is going to be. So having a team dedicated to that, having sort of an open-ended research project as far as how much extra thrust could we get out of one of these commercial off-the-shelf engines, figuring out how to do the structural design, and so on. Initially, we planned to have sort of initial aircraft design finished by the summer, August 21st, so this week. So that way we could have the bulk of the work done prior to people going back to school and presumably having a drop-off in attendance and availability. As you can see in the next chart, we decided that that was slightly aggressive. Originally, we wanted to fly early next year. And as we've sort of gone through, learned more, done some more calculation, designed, we've decided to go with this two-phase approach, which is, broken up on this next slide here, where phase one is building the fastest air-breathing RC craft that we can. The current record is set by some Germans at in like the Mach 0.64 range, something like that. And so we're currently planning on completing that design and getting that built to fly early next summer, hopefully. And then phase two of that is we have hopefully renewed activity next summer with at least as many or perhaps more people next summer to work on transitioning into a supersonic aircraft and all the extra difficulties that that's going to entail. So with these sort of plans and ideas, the next crucial thing was to get people who wanted to do it. And so Colin will talk a little bit more about how we got so many people from around the world.
Yeah, thank you, Cole. So after Cole and I validated that our mission wasn't an impossible one, surely a challenging one, but we were confident that we could give it a good shot. We started to reach out to people that we knew personally at our own respective universities. So within a couple of weeks, we had a team of about 15 engineers on the project, mostly from the Oklahoma area, because that's where both Cole and I are from. And then next, I went to work sending out emails to engineering clubs and faculties from universities all over the United States. The results were mixed, as they always are. Some people were very keen to express their excitement about the project, and others were just as keen to express their doubts. However, we trudged on, continued to grow our team with new people from all over the United States joining almost every day. Unbeknownst to us, however, we were about to go through a major growth spurt. On the night of June 30th, I made a post on Reddit asking for people interested in joining the project. When I woke up in the morning, I had over 100 emails from students located all over the world interested in joining the team. So that's now how we have a team of over 195 members. We're going every day, 20 different countries around the world, and more than 70 universities are represented. It's truly a diverse team that allows us to communicate people with all around the world that we would usually never have that experience. So it became very clear, very fast, that it was time to get organized and set up a leadership team. So we created the appropriate subsystems and began having weekly meetings to stay directed towards our final goal of building the supersonic RC aircraft. So this chart you see here, and Cole will elaborate on it, is how we divided up our team and the different responsibilities for each subsystem. Cole?
Right. Yeah. So in another way of looking at this chart is sort of a required competencies to meet sort of those Gantt chart goals that we had. So within propulsion, we need to get as much thrust as possible. So having people knowledgeable in turbojets, potentially rockets as well for rocket augmentation, people who are capable at doing computational fluid dynamics for both aerodynamics and combustion. CAD people, of course. For aerodynamics, similar sort of thing. We need people who are strong at hand calculations, CAD, CFD. Avionics is where we sort of push the envelope as far as what's considered an RC aircraft. And to get this very fast aircraft that potentially is flying very high, controllable, all the hardware and software needed for that. Structures, manufacturing materials, having people strong in those areas was really crucial as well as the analysis portion of that. Stability and control, people who have a little bit of experience actually getting aircraft to fly and knowing that iterative process and sort of the test steps that we need to take. And then finally, systems integration to tie it all together, especially be concerned with how things are going to fit, and making sure that we're staying safe throughout the process. And yeah, so this is the team of people that we assembled to sort of fill those goals. And I think maybe Colin had something to say towards these.
Yeah, so we built out our leadership team from students all around the United States. So we have students from Purdue, Berkeley, Oklahoma State University, University of Oklahoma. Those are our main schools for our leadership team. And then moving on, we also found it very important to build out a team of advisors, which is continuing to grow every day as well. And they have been a key part to our mission. Like today, this presentation was helped and organized by Aldo Martinez, one of our advisors. So these people have been crucial to our success, and we're very thankful that they're willing to help us out. Just going on to the next slide. Cole's going to talk about how we kind of deal with our task management, because with a team this large and dissociated, it's a really challenging thing to do.
Right. Yeah. So the unique part of this, or maybe not, it's not all unique, but definitely challenging, is that we're international, online, and voluntary. So we tried to kind of standardize how we give out tasks, which we call bids. And that sort of reflects that we're soliciting people to participate, as opposed to assigning people things that they have to do. It kind of goes into the sort of voluntary culture that we have. So you can go to the next slide. And so this is sort of the timeline that goes through these bids. So we as team leads, and even the members as well, contribute as far as what are the needs and requirements for the design. We formalize into like a PDF bid to send out. We usually organize teams on the order of like 4 to 10 people, depending on the size of the task. And then they spend usually about a week doing research, design, whatever it may be, to fulfill that bid. And then at the next weekly meeting, the sub-team meeting, they'll have a presentation. So sort of little mini design reviews is sort of the model that we have. And then we as team leads take all those different design review decisions to sort of guide the overall direction of the aircraft. And so, yeah, another major part of this is being able to perform the work. So you definitely probably saw on the chart needing CFD, CAD, a lot of software intensive things. So we've got very generous sponsorships from SolidWorks, Siemens, Rapid Prototyping. For SolidWorks, that's what we've standardized our CAD to for the aircraft design. Siemens, we use Star CCM for CFD within there, as well as the structures team has been using NX for their CAD because it very nicely integrates with the composite analysis and such, which our team lead will talk about a little bit more later. And then whatimbuilding.com is sort of a brand new website that's come about, and they provided the funding for us to get our very first engine and start to do some testing. That was actually crucial to the sort of Reddit marketing push. So that's very important as well. Yep.
Awesome. Yeah. So, well, as engineers and engineering students specifically, the first thing we want to do is start building stuff. But it very soon became clear that the governments in our world will not just allow you to fly a drone at 17,000 feet and 700 miles per hour without asking permission. So, however, we didn't let this deter our efforts. Instead, we picked up the phone and started calling the Federal Aviation Administration. After many conversations with some very confused FAA employees, we finally reached the Tactical Operations Support Group office, and now we're working with the 2 FAA officers to ensure that when our aircraft flies, it does so safely and legally. So the next issue to overcome is the possibility of ITAR and EAR regulations, since we are an international group. This was an important topic that we considered to make sure that we are following all US laws. After scouring the US munitions list, which is not a fun document, and obtaining a consultation with FD Associates, a professional export control consultancy based in Washington, DC, our team is confident that given the design of our aircraft and the context of our project, we are working within all US regulations. So now we'll dive into our design, give you a little bit more context and specifics about our aircraft from all of our subsystem leads. So let's get started.
Hey everyone. So just as a reminder, as we go through these subsystems, I'd just like to remind you that this work is a result and effort of our team members. They've worked very hard over the summer to advance this project, and I hope you all enjoy the work they put in thus far. So I'm Abdurrahman Manzy, but my friends call me Man. I'm the main man for Propulsion, I'm a recent grad from the Oklahoma State University with degrees in both mechanical and aerospace engineering. This fall, I'll be continuing my education at Oklahoma State University, pursuing a graduate degree in aerospace engineering with a focus on UAS development. I was heavily involved on campus during my undergraduate career, ranging from undergraduate research to my college student council. My interest in propulsion was spurred with my interaction with Cole, my participation in our senior capstone project, experience working on a hybrid turboelectric propulsion system for small-scale UAS. Next slide. So, what does a propulsion team do? Well, it's pretty self-explanatory. We bring the boom. We're responsible for designing and testing the propulsion system for the aircraft. Our goals for this project include analyzing and testing our mission jet engines, which are the Frank turbine FE250 and the JetCat P400. Design a properly sized inlet for the engine. Design and optimize the exhaust nozzle for the aircraft, as well as design any augmentation to the propulsion system in order to get us past Mach 1. Our primary option being a custom afterburner, and our secondary being rocket augmentation. So, as Cole mentioned earlier, one of the major problems with designing a supersonic UAS is that UAS engines are very restricted by their physical size. There's currently no off-the-shelf RC jet engines that can take an aircraft past Mach 1. Next slide. So for the so as we mentioned earlier, the FT250, it produces a thrust of 60 pounds. In order to get us to Mach 1 with that engine, we would require a 50% increase in thrust. This is highlighted in the graph to the right with the blue line depicting the thrust required from the engine, and the red line showing the total thrust available from the base engine. And as you see the jump, this includes a augmentation of 50% increased thrust to the engine. Some other issues that we have found in designing aircraft or concerns is that the complexity of designing a small scale augmentation system, such as an afterburner, fabricating some of these complex components may be difficult with our current abilities. Additionally, the UAS engines usually use a centrifugal compressor, which aren't really designed for high Mach speeds. And if we want to address these challenges, we may literally become project doomed. So looking at some of our preliminary designs to answer these challenges, this summer we came up with some designs for the aircraft inlet, exhaust nozzle afterburner, and an integrated rocket augmentation system. So for the inlet, we went with a pitot inlet and S-duct with the goal of slowing down the flow for the compressor so that it can operate well. We also designed an optimized nozzle using an engine performance analysis, as well as using simulation with computational fluid dynamics. And after as other things we've done is also design a simplified afterburner, which is shown down there. We did this by performing a rudimentary engine performance analysis. We went with a relatively simple design, just because scaling down a full-size afterburner is not possible, and there'd be too many complex components that we deem would just be too unnecessary. And we'll be going with a system where we start simple, and if there are any needs or issues that need to be resolved, we will add those on as testing progresses. Next slide. So our next steps. So with a detailed design of our afterburner coming soon, we will be transitioning to a more testing phase. So as you can see to the right here, we have our humble testing stand with a King-Tech K70 engine. We'll be using a K70 engine because, as Cole mentioned, we were able to acquire funds to purchase this engine, and this engine will serve as like a proof of concept for our afterburner. This will show us if it's even possible for us to get a 50% increase in thrust for any engine. We'll be also working with industry professionals to improve and define our afterburner design and to ensure that we have a reliable system that can accelerate our aircraft past Mach 1. We appreciate all of you for listening to Propulsion Subteam, and Johnathan will take it away from here for Aerodynamics.
Okay, so my name is Johnathan Burgess. I've had a little bit of connecting difficulties, so may have to deal with that. Apologies in advance. But I just recently graduated from Oklahoma State University with Cole Replogle and Mann Mansy with a Bachelor in Science degree in Aerospace Engineering, and also got one in Mechanical while I was there. I'll be returning, well, I'm actually at OSU right now, returning this week to get my master's degree at OSU, continuing what we started on our senior capstone project, working on turbo electric propulsion systems. So for Project Boom, I'm the aerodynamics lead. And so I'm basically over just kind of sizing the aircraft and the overall shape of it and figuring out how that shape interacts with the airflow. On a personal level, I enjoy hanging out with my kids, surfing, being outside and with family as much as I can. I've got a 6-year-old boy and a 2-year-old girl. Okay, next slide, please. So as Mann said, we pretty much knew, Mann and Cole had come up with a pretty good idea of maybe the thrust that we could expect from an afterburner turbine. And so we had that, and we've had the fuel burn that we could expect. And so basically from that point, the aerodynamics team had to figure out what size aircraft are we going to have, and like what's it going to look like, all of these things. And so we started to run some mission analysis. I came up with a Python program there that I developed to do an emission analysis on our aircraft, and a couple of constraints began to pop their head out pretty quickly. Basically, we realized that we could only have a certain size wing, because the larger the wing, the more drag that we had. And so up to a certain point, we couldn't get any larger than that because of the amount of thrust that we were expecting. So we immediately had a wing area constraint that we've used for basically the beginning on of 0.350 meters squared, for example. Another thing that popped out was basically the efficiency of the overall aerodynamics of the aircraft, which is the seating knot, or the lowest drag that you could expect, lowest drag coefficient. And basically another number popped out that probably doesn't mean anything to or doesn't mean something to just everybody, but 0.013 popped out as a maximum. And what that basically means is we almost have to be aerodynamically perfect, almost no drag, excess drag, or anything like that. So obviously, if you need to go fast, you need to be streamlined. And so that's just kind of some of the things that we figured out. Also narrow down what type of day we want to fly at, what altitude are we going to fly at, given 17,000 is our maximum, 17,000 feet. Some things like that. Obviously, you could go down to the smallest wing area as possible to just a fin, basically like a missile, and why not? And so one of the things is the smaller the wing you have, the higher your V stall, or you stall at a higher speed, the smaller your wing is. And so we don't want a high V stall to a certain point. So we constrained our wing shrinkage to a certain V stall maximum, or maximum, which was 35 meters per second. And so basically that's just some of the things we use to get an idea of where to start with sizing and the shape of it. And so from there, next slide, please. This is just a validity check that we asked a couple of, we try to look at the mission constraints and the mission analysis from a couple of different standpoints. This is a mission constraint diagram using some of the same values that Cole and I ran as a sanity check, and everything checked out. As you can see, we have an insane maximum climb rate of 6,000 feet per minute, but I think we have like a 2-to-1 thrust to weight ratio, so kind of can be expected. And so, yeah, so that all checked out, everything looked good. And so from that point on, we kept moving forward. And as Cole and Colin alluded to before, there was literally like an overnight change in this project, where we went from about 10 people solid to about 100. And so when that happened, next slide, please, we had to figure out basically what do we do with all these people and how do we go forward. And so one of the first things we did was, as a project, was come up with Aero Bid 1, the aerodynamics first bid. And so we took about 40 new members and split them up into 4 different groups, about 10 per group. And we gave them 4 different design concepts to come up with in about a week to do it. And so there was a subsonic and 3 supersonic designs. And up to this point, we only had the drawing on the bottom right of the corner of the screen there. And that's the only thing we had was just preliminary sizing and literally a drawing that we had on paper. And so after this week and a half that these 40 new members went in and worked on 4 separate concepts, we had immediately 7 different concepts to choose from and all of their corresponding CAD files. So we went from a drawing and then 9 days later having 7 different concepts to have to down select from, which was a really great problem. And immediately what happened was we had like 2 or 3 things that we couldn't choose from just right off the bat. So we took 2 of those and started to kind of massage them around in the supersonic profile. And then we took some of the subsonic stuff and kind of kept looking into that. And so as you can kind of see what the progression of that, it was from the hand-drawn drawing and then it went to the 4 bids that I just mentioned. And from there, we took the Bravo and the Charlie as our favorite for the supersonic design. And I'll get more into this in just a minute, but from there, we started to look at different turbine options, a 250 thrust turbine, as well as a 400, and the resultant aircraft size and fuel capacity requirements and all of that. And so right now, we've just kind of decided on the B250 as our first phase. So we've taken a lot of things that we've worked in on both of those. They're basically the same aircraft. They're just intended with different thrusts, different power plants, basically. And so here we are at phase 1. And I know Cole and Colin have kind of spoken to this already, but phase 1 is meant to be a subsonic proof of concept. And so we're going to prove our concept up to basically Mach 0.8, make sure it can fly, can survive it, the transition period and the transonic stage and back down. And then for phase 2, we're going to take basically the same thing. And if we have to scale it up or whatever, add rockets or an afterburner, try to go supersonic. Next slide, please. And so once we had Bravo and Charlie, we needed to do a wing analysis separate from the fuselage. So what we did for quite a while is we just looked at the wings by themselves and we did some analysis. And one of the things that we figured out was that we wanted a delta wing because of the low drag and the ease of manufacturing and the structural rigidity of it. Because we knew we needed a small wing, but it still needed to be strong enough to not break. And so if we had a real long or rear swept wing, it potentially could have structural issues. We're not going to use the wing for much fuel capacity anyway because of how thin it is. So basically we do that. And so what we did was there's multiple different delta wing configurations out there. We started to compare them all and we came up with a cranked wing and an arrowhead wing, which is on the right. For me, I guess it is you. And the cranked is on top and the arrowhead is on bottom. And basically the reason why is they provided the lowest amount of drag from the other deltas. And that we chose the cranked because it was the most forgiving with different angles of attack. The aerodynamic center shifted less. So we've decided to go with the cranked wing, even though it's slightly draggier than the arrowhead wing based on our analysis. Next slide, please. And so once we had the wing and we had a fuselage that we chose, we started to integrate them together. And if you do or don't know, one of the things that you need to adhere to or at least take note of if you're trying to go through the sound barrier is what they call the area rule and your adherence to the Sears-Hack curve as an example. And so this is kind of some of the progression that we've had in the aero department for following the area rule. And as you can see on the top right, that's kind of where we started. And then at the bottom, this is kind of like our iterative process to get to where we are now or to where we would want to be. And so for this, you may not know what it is or how it got there or what the area rule is. So basically what it does is it analyzes the cross-sectional area from the nose to the tail or vice versa of the aircraft. And it's supposed to follow that curve. And so the dotted line is the one we want and the blue is our actual. And so a couple of our members figured out a way all on their own and completely unprompted how to create a macro that works with SolidWorks and MATLAB to plot this. So they've been using it a lot. Great job, you guys. It's just an example of something that's, come from this, that's not exactly what we were expecting, but it's a great tool. So next slide. One of the things too that we've been looking at on the aerodynamic side and kind of pairing with the propulsions team is the inlet design, because there's a lot of different ways we could go with this. One of the benchmark, or one of our competitors potentially out of Florida, they were going to leave their turbines completely exposed to the free stream, and that's probably one of the reasons why they didn't succeed. Because when you go through the sound barrier, you're going to have to deal with shock waves. And so if you design the inlet incorrectly or not at all, then you can potentially damage your turbine, stall it, things like that. Bad things can happen. And also, if you design it correctly, we could actually increase our performance at our design point. And so this is an inlet that we've been working on. It's kind of modeled after the Tomahawk inlet. I won't spend a lot of time here because Mann and the propulsion side has probably already mentioned this in more detail. And so I'm probably going to just talk about the fact that we have to adhere to the area rule again through here or with the inlet design, and we just have to take note of that. And we also have to worry about the flow through the bird. And so this is basically the Bravo design. The top left is the initial CAD drawing that was drawn from the hand drawing that we had. And then from the top left to right and then down, that's kind of the progression. And so you can see where there was a major change on the bottom, and that's where we went with Bravo, but we decided to blend Bravo and Charlie together, which was from our first bid. So as soon as we got all of these members, there in that first bid, we still have products coming from that, some great things that we've learned and continuing to expand on. So I just wanted to show that a little bit. And so now this is where we're at with our current aircraft. It's been blended again from Bravo and Charlie. And so this is just shows basically the iterative process. This is a model from our augmented reality team also. This is normally manipulable. And so that's a props to them, because we probably won't talk about them much, but we have an augmented reality team that's done really great. And so what's next for the Aero team basically is right now, tomorrow and tonight, we are starting a foam model build. And so we're going to try to take a full scale 1-to-1 full model, a foam model, and try to fly it to, prove out that our V-stall is where it should be, and prove out where our CG placement is, the stability control of the aircraft and things like that, and the maneuverability. And then also we plan on having our avionics man or guy come in from Berkeley and try to fly this foam model with an autonomous flight controller. And so we can hopefully prove all that out within the next month or so before we ever actually, try to go into some real manufacturing or anything. So talking about a little bit of Stabcon is, trying to prove that out and everything. And so we're going to do that through the foam model. And speaking of that, I think next we have the Stabcon lead, Skyler, who's going to talk about how we're actually going to control this thing.
Sweet. Thank you very much, Jonathan. I really appreciate it. Hello, my name's Skyler Jacob. Go ahead to the next slide, please. And I am the stability and control lead for Project Boom. I'm a super senior at Oklahoma State University studying mechanical and aerospace engineering. I'll be pursuing a master's degree in aerospace with a focus on UAS structural design beginning in the spring. I've participated in 4 speed-based design build fly competitions, so I'm very excited to be part of a much more massive speed-based design. And I really enjoy camping, hiking, and cinema in my free time. Now, next slide, please. Before we really get into the details about the technical Stabcon issues we'll be dealing with for high transonic and supersonic design, I'm going to first explain a little bit of the basics of stability and control. Next slide, please. Aircraft stability and control are well intertwined, and they both have 3 axes of motion that we're concerned with. Longitudinal, which is also known as pitch, lateral, which is also known as roll, and directional, which is also known as yaw. Longitudinal stability is the most important for us in our design phase because, as you can picture, it's what keeps our aircraft flying steady and level. which will be important as we want to keep the drag low and to increase our max speed. This is measured by the static margin, a non-dimensional value of the placement of the CG, or the center of gravity, compared to our center of lift, which we will plan to keep around 10 to 15% so that we're still stable yet controllable. Next slide, please. Next is the lateral stability. This is shown by the image, and it is designed to prevent the aircraft from rolling from one side to the other. While this is not directly a drag relation to our aircraft, flying upside down is not really the nominal position, as it puts your lift in the wrong direction. This is often controlled by the wing in order to keep your body facing up by either using sweep, dihedral, or vertical wing location. Next slide, please. And the last of our stability sections is directional stability. This is what will keep our aircraft moving straight. Now, this is crucial since an angle of side slip will increase the perceived frontal area of our aircraft. This is achieved by using vertical stabilizers to increase the amount of area on the rear of our aircraft. It's exactly how a weather vane works, using what is called a weathercocking effect. From there, we'll actually go into our controls. So next slide, please. So what the controls do is they will disturb the stability surfaces in order to change the direction of flight of the aircraft. These will match up type for type with our stability axes we're using. For our aircraft, due to the delta wing design, the basic layout will be shown to the right. While this is not an image of our aircraft, it is one most people are familiar with, a fighter aircraft. For the longitudinal stability and control of our aircraft, this will use elevons and canards as highlighted in red on the rear and in red on the front, respectively. A canard is a small wing-like surface on the front of the aircraft, while elevons, which are the surfaces that, while elevons, which are surfaces that change the lift of the wing. The pitch will be controlled by the elevons moving in the same direction, and the angle of the pitch will be controlled by the elevons moving in the same direction, and the angle of attack of the canard. The roll control will be achieved by moving the elevons in opposing directions, while yaw control will either use the rudder, the red highlighted surface on the rear of the aircraft, or a yank and bake maneuver that is a mixture of pitch and roll to change the direction the aircraft faces. Next slide, please. Those surfaces have been chosen to counteract some of the major problems we'll be having our aircraft see at high subsonic and transonic speeds. At these subsonic speeds, the aircraft is going to have a high stall speed, which is generally unwanted because the stall speed is the speed at which you lose lift over your wings. And your lift does not equal the weight of your aircraft. These higher stall speeds are due to our small wing sizes. This in turn will decrease our control authority at our low speeds. This mixes in with the need to keep our static margin positive between 5 to 15% in order so that we're stable and controllable, as mentioned earlier. In the transonic region, the aircraft will encounter Mach tuck, which will cause the aircraft to pitch down drastically due to the velocity and pressure differentials over the wing's upper and lower surfaces. This region will also cause and force flutter, which is an aeroelastic effect caused by the turbulent flow over the control surfaces. This can create unexpected forces that will prevent the surfaces from being controlled or even break them from the wing. Next slide, please. This leads us to our chosen preliminary Stabcon configuration. Our aircraft will have elevon surfaces on the inboard of the wing and a control canard at the front of the aircraft. This is pretty similar to how the XB-70 Valkyrie, which is a sick plane just to begin with, if you don't know it, please look it up, where the canard doesn't add much additional lift on the front. That way, it doesn't move our aerodynamic center or our center of lift forward much, as it acts as an all-moving stab. That way, it'll change the angle of attack of the aircraft during the transonic region. This will allow us to counteract both Mach tuck and flutter. The final surface is the vertical stabilizer, which will help keep our aircraft facing forward during flight. The direction of flight will either be changed using a rudder or a yank and bake maneuver as talked about on the previous slide. Next slide, please. This leads us to where we need to go as we move on. The largest of these is knowing exactly where our static margin is, because a change in 1 to 2 centimeters of the center of gravity of your aircraft can drastically change how your aircraft moves around in the sky. This will be achieved by narrowing down the precise location of that center of gravity and using our VSP model and calculators that the amazing team members of the Stabcon team have developed to actually nail down our stabilizer sizes and our control surface sizes. That way we get a good center of lift of our aircraft. From there, we will choose an airfoil that has a low drag and a low lift for our canard. Then we will design how the control surfaces will be actuated by picking servos and motors to maneuver those surfaces and place them within the aircraft. After all that is done, we will have to then use our stability derivatives, which is this huge, ugly matrix of numbers, and find those constants for our 5 modes of flight. That way we can give the inertial matrix and aerodynamic characteristics to find our common frequencies for our aircraft that avionics will have to use later down the line. That way they can actually control how our aircraft reacts to some of these air forces. Now that this roll has come to a stable stop, why don't we turn it over to structures where they can pitch us their plans? Thank you. On to you, Gaurav.
All right, thank you so much, Skyler. Hello, everyone. My name is Gaurav Jalan. I am a graduating senior from the University of Manchester with an ME in mechanical engineering. I'm also currently based in the UK, which explains why I'm engulfed in darkness over here. But yeah, moving on. During my time at uni, I worked with competitive DMTA groups on campus, such as the Manchester CatSat project and underwater robotics at Berkeley as a design engineer. And I've also interned with research organizations focusing on UAV control. Finally, I'm delighted to be here as the structures lead for Project Boom, showing off the work done by our lovely members. Next slide, please. I would like to start by just giving an overview of the tasks of the structures team. And to start with, as our chief engineer would put it very eloquently, the role of the structures team is to make our aircraft not break, which is true, but there is a bit more to it than just that. So we shall first look at overall considerations for the structures team, and I shall explain why I have placed some in different columns shortly. So number 1, withstanding design loads without catastrophic failure. So this involves determining load cases for our aircraft, which depend on maneuvers we plan on doing, wing loading, etc., to carry out stress analyses on. This also takes the reliability of various mechanisms into account. Number 2, static strength requirements. So this involves meeting requirements such as having at least 3 seconds before catastrophic failure occurs, on being subject to ultimate load limit, among others. And number 3, stiffness and flutter. So minimizing flutter to maintain aerodynamic performance, expected aerodynamic performance, and fatigue resistance, among other reasons. So due to the conceptual stage of our design, these are the design factors that have been the major focus of our work until now. We will be putting higher focus on factors such as crashworthiness, which deals with issues such as protection of avionics and the fuel tank from rupture in the event of an unexpected crash, and the others mentioned in the right column, which are pretty self-explanatory over the coming weeks. Next slide, please. So what choices does the team make to achieve these goals? I'm going to go over a couple of the ones that are mentioned. So material choice, internal structure architecture, and how we place our critical components. So by placing components strategically, we can make sure that no one section of the aircraft experiences unusually high stresses. This positioning and analysis of load conditions for various maneuvers will guide the internal structure architecture. So for example, placement of bulkheads, number of stiffeners, etc., and ultimately our material choices as well. On the right side of it, I have listed some unknowns which are specific to our project due to its uniqueness. So manufacturing prowess that will be available to us. This is something that we are still looking into. This is going to depend on things like how much funding we have to be able to explore third-party manufacturing, or if we decide to do this in-house. And this also ties into the second point, which is financial headroom for conducting tests. And number 3, which is team manpower stability, which again is unique to us because of the voluntary nature of our project. Next slide, please. So how do we fit into the flow? So the aero team designs the exterior shells that meets our mission and flight criteria best. So for example, wing max thickness, fuselage and wing profile, nose cone shape, etc. The Stabcon team works alongside to size control surfaces and determine the range of motion required for these control surfaces. And then these design constraints are fed into the structures team, where we determine the feasibility of the design and update the aforementioned teams if any changes need to be made. For example, having thicker wings to be able to withstand our expected wing loads. And we continue to iterate from there. Next slide, please. Next slide, please. Sorry, I think we're having some technical issues. Okay, there we go. So due to aero design still being in a bit of a conceptual stage and having more concrete designs literally as of 2 days before, the structures team has mostly been focusing on developing tools to aid with rough sizing of components to be able to move quickly once aero dimensions are more concrete and load cases are established. This has been the focus of bids 1 to 2, as can be seen in the diagram. So the basic idea behind developing the wing analysis tool, as mentioned in the bubble of bid 1 and 2, is to be able to produce a more educated FEA model. And FEA is by far the sharpest tool at our disposal, but it takes time and experience to set up correctly. So making frequent changes to those models is time consuming and inefficient. So that kind of explains our reason for developing these tools. With the latest bid 3, which is mentioned on the right-hand side, we also started to look into materials available, manufacturing techniques, etc. The team set up decision matrices to evaluate various options, identified rough constraints, providing us with a good tool to make our choices in the future. We have also set up a small team to start working with Siemens NX, which we have selected to be our analysis tool of choice, just because it combines CAD, FEA, and composite analysis under one piece of software. And it also just makes it easier to have the same software across all of the members and not having to deal with issues of just models being compatible and things like that. So next slide, please. Over here, we have some examples of the work done by a lovely team. So starting from the left, we see a VN diagram made for a previous iteration of Bravo. So we took some industry standard margins of safety and ultimate loads into account. Then the other two are a span-wise shear and bending moment produced in the wing, which are from our MATLAB tool. Next slide, please. We also, on the left-hand side, we also see a decision matrix evaluating our various material choices. And then on the right-hand side, we have some sanity check FEA, which has been done by our bid 3 team. Next slide, please. So finally, some important technical challenges that are ahead of us. As Skyler briefly touched upon, the unpredictability of loads and vibrations in the transonic region make for some tricky analysis. FE models, more so with the involvement of composites and multiple interacting surfaces, are tricky to set up, for which reason we have a small team, as discussed earlier, working on reproducing results from existing papers to get a feel for these analyses. Harsh landing options, such as having a net capture, which is essentially a high impulse loading case, would be tricky to analyze. Next, design of possible retract and control surfaces would be an interesting design challenge due to a high reliability requirement and the scenario of it being used at high speeds. A big manufacturing challenge would be mold design, so getting pieces to line up precisely, the molds themselves, which are very time and resource intensive to produce. And finally, designing tests that give us a good idea of what the performance of the structure is going to be like in real flight. So that brings us to the end of the work being done by the structures team, and I shall hand it to our avionics lead. Thank you.
Thanks, Gaurav. Next slide, please. Hello, everyone. I'm Minos, a systems lead for Project Boom's avionics team. I am a graduating senior from University of California at Berkeley with a degree in computer science. I have a background in robotics research and data and general software engineering in the CS field. Lately, I have been interested in finding novel approaches to solve problems using computation, validating them with experiments. I am excited to share some of the progress that our amazing avionics team members have made over the summer and to update you all on where the avionics team is headed. Next slide, please. First, I want to give you an idea about the folks in the avionics team. Our team consists of about 20 members from more than 7 different time zones and 7 countries. With our members' hard work, the avionics team made a significant progress over the summer, some of which we will be going over in the following slides. What do we do? The avionics team is involved in building a safe, robust, and autonomous avionics system. Our team works from the ground up doing components specification researches to writing autonomous controller and running systems level simulations with experimental validations. So today, I'd like to share some of the work our team has put on amazing work into. First, I'll briefly go over the concepts of autonomous navigation. Second, I will present the challenges we ran into during components specification researches. And lastly, our SLS, the systems level simulation for validating our functional and performance characteristics at the components and subsystem level. Next slide, please. Why autonomous navigation and control? For our mission, it is crucial component in part due to our mission profile. As of now, for our sound barrier breaking attempt, we will be flying at about 12,000 feet with a maximum altitude of 17,000 feet. Because we are flying high and fast, a pilot on the ground will not have the necessary ability to fly the vehicle with a typical RC piloting setup. Further still, the pilot may lack the ability to react to the conditions that are hard to observe through the instrumentation measurement telemetry. Thus, our need for an autonomous navigation and controls on board the vehicle and a fly-by-wire manual control for the safety pilot. How does a human pilot controls an RC plane? Humans have 5 senses that we utilize to interpret the physical world we are living in. And an RC pilot would predominantly use the vision by either direct line of sight flight or through an FPV, first person view system to fly the vehicle. Compared to that, how would a machine fly an airplane? Next, please. It uses sensors. For example, an IMU sensor pictured here measures acceleration and angular velocity in each of the 3 axes. Sensors can measure things to the accuracy a human cannot possibly achieve or outright cannot sense. However, a machine using sensors lack a high-level cognition that humans can perform nominally on a day-to-day basis. Yet, going from point A to point B is a simple task for a human. Next slide, please. However, for a machine, it's a process that involves a state estimator, a controller, and a feedback loop. And that's what we use in combination with the sensors to control our vehicle safely and autonomously. In the above image, we reference an attitude controller that we are using for a straight line path section of the mission. Next slide, please. This is our components diagram updated as of this Monday. Safety and mitigating risks are our top priority. Therefore, we have conducted thoughtful researches on possible conditions and scenarios that our vehicle may be subjected to during the mission. Based on the information, we've carefully selected our components that can nominally perform even in the low probability scenarios. For mission critical components like IMU and GPS, we have considered the state estimator convergence and sampling aliasing. The primary IMU for the phase 1 mission is ADIS 16470 from Analog Devices, which has an excellent data output rate, run bias, stability, and noise density. For GPS, we have selected a real-time kinematic GPS unit that gives us a centimeter accuracy with a ground-based station for RTCM corrections. Next slide, please. Now, system simulation is useful for a variety of reasons, and for our SLS, it is particularly useful for testing all functional and performance characteristics at the components and subsystem level. For example, we can test the performance of autonomous controller with the simulated sensor data. API at a lab that I work in said a simulation is always bound to succeed. This is true for our SLS as well. And to make the simulation useful, we need to be aware of its limits and know how to improve the physics and simulation fidelity to the degree that we can accept the simulation results. For SLS, we are using JSB Sim, an open source flight dynamics model library that is highly extensible for modeling the vehicle, and Flight Gear, a flight simulator, and have the flight controller run in a software in the loop simulation that interfaces with the simulated world and have it actuate the controls. We will continue to improve the simulation by emulating the physics during the transonic regime, as well as use the flight data from the test flights to measure the performance. Next slide, please. So far, we've shared Avionics team's progress from reasons for our choice in the autonomous navigation and control, challenges in component specification, and a scheme to measure the performance at the components and subsystem level. Our next steps are to increase the simulation physics fidelity for the transonic regime, collect data and validate the SLS with real test flights, start the process for acquiring components, iterate through our design process with SLS results, and use SLS hardware in the loop simulation for pilot training. Now I will hand it off to our integrations lead, Jake Compton, who is joining us from an undisclosed yet beautiful location. Jake?
Hi, I'm Jake Compton, and I'm the integration lead for Project Boom. I'm currently a senior in Purdue University Aerospace Engineering. I was really hoping to be able to make it out to our town hall today, but unfortunately I'm kind of out on a road trip right now. So I just wanted to take the opportunity to share some of the beautiful views of our world with you guys. Thanks. Hi, I'm Jake Compton.
Yeah, so as you can see, Jake is doing his best to escape industrialized society at the moment. That's a nice thing about Project Boom is our time off is very generous, though our pay and benefits are lacking compared to other industry competitors. But yeah, Jake's a stud. He'll be graduating from Purdue this year. It's a couple internships at Jacobs and General Atomics. Overall, a really smart guy. He's focusing in propulsion, I believe, at Purdue. So it's your aeronautical and astronautical engineering. But yeah, propulsion is his focus with that. So what does Jake cover? Is the systems integration team, which is meant to pull it all together. So this was sort of a catch-all sort of group that I formed to make sure that nothing is slipping through the cracks. They're in charge of things like component placement and the center of gravity calculations that they interface with the other teams on. Monitoring safety and compliance, so making sure throughout the design process that we are still fine by FAA and ITAR standards. Researching into takeoff and landing, and the different strategies associated with that. And then looking at rockets, as we've kind of sprinkled throughout, we've actually, it doesn't really hint at how much work we've actually looked at looking into rockets. But the integration team has done a really great job at identifying all the challenges with adding rockets to our plane. So next slide. So the unique challenge with integration is it's so fluid. So rapid iteration means having to update component layout and center of gravity spreadsheets on a daily basis, if not an hourly basis, if we're actively working on things. And that requires constant collaboration between the integration team and everybody else. So next slide. Yeah, major thing is component layout. So you can see here is sort of a mock-up of the component layout for the B400 variant. So that has the JetCat P400 engine in the Bravo aircraft variant. So you can see putting all the avionics in the nose, fuel tank as close as we can to the center of gravity, and then the engine out the back. And you'll notice the engine has moved forward a bit, and that's to help out with our center of gravity, as well as it makes it a little bit more interchangeable with throwing in an afterburner. So next slide. You can see here basically the same thing for the B250 layout. Pretty much looks identical, except if you're really keen, you notice that things are a lot more packed down in the nose here, and there's sort of floating a little bit more space in the B400. That's not necessarily a bad thing. That may mean that this variant is a little bit more tailored to the space that we need. So next slide. I believe the labels on these are actually flipped to where the B250 variant is on the left and the B400 variant is on the right. But you can see that the structure's weight is about the same weight between the two. That may not be a great assumption, but we'll be moving through that. But the big difference is the added engine weight and the added fuel required. And so a really big challenge we've been looking at and trying to pay close attention to is not so much just the weight added from the extra fuel that we need, but where we're going to store that. So a volume problem. So that's kind of where we're at as far as looking at the integration for the two aircraft. Takeoff and landing is an active area of research for us. I think we're converging towards solutions there. So basically, again, it's all a volume and weight sort of game, where if we can externalize our takeoff and landing to the ground, to where we don't need to carry a parachute, a landing gear, anything like that, then that's preferable. So we've looked at, there's a lot of different takeoff options, and we'll likely have way more runway than needed. So takeoff isn't really as big of a concern as landing. So we've talked quite a bit about how high our stall velocity is, around 35 meters a second. I wouldn't want to be standing near that personally. So getting that to land with such a high stall velocity has been challenging. So I've been looking at net. Gaurav touched a bit on the structural implications of that. We're still sort of rolling through whether that's feasible or not. A conventional landing gear, conventional in the name is generally good, but it adds some pounds and then takes up space, obviously. A deployable parachute, again, takes up a good amount of volume, but it's an option we've pursued as well. And then, so again, we're continually looking at ITAR FAA breaches. And then as we go into phase 2, we'll be looking at more rocket integration set. So I have some nice Python programs set up dealing with selection of rockets and sort of how they're timing the lighting will work out, but that's a little bit postponed for now. So that's going to wrap up the vehicle design portion that we're going to share with you today. Of course, I think we're doing okay on time as far as we should have some time for specific questions. We'll be happy to answer those. But now we're going to have Shiva, who's our marketing lead, sort of talk about that aspect of the project, which is super crucial and benefits the rest of the project, and is a large reason of why we're able to talk to you here today. And he's been in charge of making this presentation look as good as it does. So turn it over to Shiva.
All right. Thank you so much, Cole. Hey guys, thanks for sticking with us so far. Each of our leads have talked about some of the major hurdles that we face and our plan going forward. So I'm here to kind of bring that all back together. My name is Shiva Vallabhaneni, and I'm a senior at Purdue University studying aerospace engineering with a focus in controls and propulsion. In addition to that, I am also a visual artist and designer and have been working on my craft for the last 5 years. At Purdue, I also work as a supplemental instruction leader for fluid mechanics. And this past summer, I've been working on a zero-gravity flight experiment payload this summer. So as an aerospace engineer with a foot in the design and business world, it's very clear to me that we are a media company before anything else. We're a media company, comma, and we are a student-led engineering design team. And the reason I say this is if you're not talking in any one of these platforms, whether that be LinkedIn, YouTube, Instagram, if you're not communicating what you're trying to accomplish effectively and differently on every platform, predicated on how the consumer thinks about that platform when they're in it, you've already lost the game. So our goal on the marketing team is to create macro content which documents the entire engineering process. Through our podcast called Afterburner and our engineering design reports, as well as articles and video content, we'll be able to accomplish this goal. As you can see here, our content is really broken up into 3 different categories. Our process, where we will be able to put online every single step of our engineering design process, starting from the first bid all the way to the last bid. Our discussion content surrounds our podcast, where we can interface with industry leaders and advisors, and also provide value in terms of design articles, which explain why we designed our aircraft a certain way, as well as providing educational content with aerospace concepts. So with all of this content, the goal is to break that down to micro content in order to really provide value for all of the students who are following our journey. And as we went on this process in the last 2 months, we really had to ask ourselves, what is the Project Boom brand and what are we going to bring to the table? And I think the largest thing is we want to be able to empower and inspire other students in their own personal journeys. So when discovering our brand, our goal was to create a brand that is professional, but also speaks to the youth of the team and the organization. The Project Boom team's core statement is, underneath it all, we're all just a bunch of kids. So in order to find a solution to this problem, we asked ourselves, how might we charge students with the initiative to believe in their capability to tackle complex engineering problems? And when thinking about that, we found our main 3 pillars for Project Boom's marketing are transparency, acknowledgement, and connections. So transparency really relates to our entire engineering design process. Our goal is to make sure that if somebody wants to find Project Boom online, they will be able to see every step of our project and see how we got from a design decision at the final version of our aircraft all the way starting from the beginning. And I think being transparent and showing our progress and showing our learning over time is something that is core to the Project Boom brand. The second thing is acknowledgement. At Project Boom, we want to give credit where credit is due, and that goes to all of our members who have spent hours and hours this past summer, and I know we'll be spending a lot of time in the future making our dream become a reality. And lastly, this whole project and Project Boom is about building connection. Whether this be connecting engineering students or students in general to aerospace concepts, connecting students to other students globally, or building a connection between the audience and Project Boom, as well as connecting industry leaders to students all over the world. More than breaking the sound barrier, this project is also about making lasting connections that will be beneficial for our team members and students and advisors following this project for years to come. Now, my design or my philosophy behind this is something that I've heard a lot online through a mentor of mine, Chris Doe. And what he says is the way to build trust is to teach what you know while you learn. And that is the mantra that we're using here at Project Boom. Now I'm going to hand it off to Colin really quick to talk about what you might be able to do to support us.
Awesome. Well, thank you, Shiva, and thank you to all the leads for presenting. So what can you guys do to help us with this project? There's a couple of things. So advisors, like we said, we have a great group of advisors and we're always willing to learn more. We're students and we're trying to be sponges and to learn as much as we can during this process. Sponsorships. The way this project is set up financially is, one, we're a registered nonprofit within the state of Oklahoma under Project Boom, Inc. And that is because we're not affiliated with any one university anywhere. And that's to allow students from all over the world to participate without having to worry about the stipulations that a university might put on our project if they were to give us funding. So therefore, all of our funding comes from private sponsorships. We've already received some amazing software sponsorships, as well as some local sponsorships for the project, and you saw those listed earlier. However, we still need help with financial things. So for some perspective, how much building a supersonic drone cost is our avionics system right now is spec'd at about $6,000. Our turbine's about $5,000. And that's for our subsonic version. The turbine for our supersonic version is closer to $10,000 to $12,000. These are all things, one, we're either looking for people to donate to our project or to raise money through crowdfunding and sponsorships. And then again, how you can help us is through promotion. We want to grow our project and let as many people hear about it as possible. So our students are working hard every day, and we want to reward them by giving them the attention that they deserve. We want to get as many people inspired as well. As Shiva talked about, a huge part of the project is inspiring other students to do this. As our team has began doing this, we've looked in at each other and said, why aren't more students around the world doing this exact thing? Why aren't there 10 design teams, collaborative global design teams working on projects, challenging problems that make us better students and engineers? So we want to inspire students through this project to do the same. And hopefully in the future, we'll see more projects just like Project Boom doing this. So you can help us through that, posting us on all of your social medias, follow us on ours. You can find us on LinkedIn. You can go to our website at www.theprojectboom.org. The before Project Boom is very important. And on that website, you can find places where you can give a personal donation if you would like. However, just like we said, sharing and getting the name out there is just as important. So now I think we're going to move into a Q&A. We've put a lot of information out here at you guys, and we want you guys to be able to ask some questions. Maybe we missed something and to elaborate. So if all of our leads can go ahead.
Just before we get into Q&A, let me just wrap it up really quick and bring it home. So Project Boom is all about breaking barriers. We're thankful that we've made it this far, and thank you today for joining us at our town hall. Hopefully you felt the same exhilaration that we all felt when we began this project. So please follow us on LinkedIn, Twitter, YouTube, or whichever is your favorite platforms online, and subscribe to our podcast called Afterburner. We will also have merch and other products coming out soon, and all proceeds go to the project. If you want to support Project Boom, please go to www.theprojectboom.org. And thank you for listening today. And remember, the sound barrier is just the destination, and this is the journey. Thank you very much.
All right, so right before we hop into the Q&A, I want to just give a quick round through the judges and see their initial thoughts and if they have any questions. And I think I'll go in reverse in the order that I introduced them. So Khushbu, I'm going to unmute you. And if you have any thoughts, recommendations on how they should proceed, if there's needs any major changes or minor changes, or how they should reconsider their design.
Absolutely. First of all, great job, team. This was definitely very inspiring, and you guys are doing a great job so far. I wish I did something like this in my school as well. Very interesting project for sure. I'm going to speak more towards the avionics, since I know that the other judges are more geared towards like propulsion and structures and such. And so in terms of avionics, I would say that I'm very interested to know what some design challenges were for avionics, and what considerations were made in like picking the IMU and some of the COTS materials, such as like the flight computer. And I wish I had more time to look at that block diagram that showed the avionics, but I mean, even after this design review, I would love to get in touch with the organization and kind of help them out with the avionics portion of it, since my background is in that. But I'm very interested in understanding the power flow, as well as the components that are being chosen for the IMU and battery, as well as there was another component, I couldn't like get the name down, but basically like have a talk about the avionics system. I noticed that there were no pressure sensors or temperature sensors that were being monitored by the avionics, which I found that a little surprising. Not sure if that was mentioned or maybe I missed that. As well as the system level testing, I think we may be using the term software in the loop. The way it was explained, I feel that it's more hardware in the loop. So I would love to sit down and kind of give like different clarifications between different types of system level testing that you could do with avionics. I would say that for a project like this, I would see some sort of software in the loop being done as well as hardware in the loop, but there are clear distinctions between the two testing. So I would definitely love to help in clarifying that and helping the team. And also like so that was like more technical stuff, but as well as like for non-technical stuff, I was very impressed that even though the team is made up of people from different countries and just different schools and different backgrounds, just coming together to get this project going, that's pretty impressive. I know some of us like who've had experiences with projects, like it was just within school and we found our own challenges, but doing it across the world, that's incredible. So hats off to you guys. Great start for sure.
Awesome. Thank you so much. Minos, if you're available, you can answer a couple of those questions right now.
I could, I sort of was frantically trying to write everything down.
Sorry, I also wrote down the questions too. And like, if you want, like I can get your email later and like, we can also do this offline if necessary, but I've written down questions.
Perfect.
Great detail. Definitely help you out with that.
I wanted to address some main points. For
Sure.
a battery, I expect based on the components and the power consumption rate. So we are including the safety margin. I expect the battery at 1 hour flight time. And based on the components that we have right now, working backwards, I've calculated that about 2200 milliampere hour battery, LiFePad battery for because we do not need high discharge rate, seems adequate for our needs. And we will have 2 of that on board the vehicle at the nose of our vehicles so that it sort of works as a countermass to our engine, and as well as provide redundancy if at all anything, a component fails or a battery.
If I may chime in, what's the total flight time again?
Right now we're aiming for 30 minutes, and I've included another 30 minutes as a safety margin.
Okay.
And as for the pressure sensor and airspeed sensor and related things, those are included in our flight controller choice. So our flight controller right now has 3 IMUs and magnetometer and barometers. And with that, those data will feed into our control loop. And you've asked a question on, before SLS, you've asked a few more questions. Could you reiterate some of those points, please?
Yeah, so it was mainly about pressures and temperatures being monitored, but that also reminded me, I would love to understand the valve actuation, how that works. Is it a solenoid? What kind of valves are being used? How that's being controlled? Is there some sort of power save happening on those valves? Because of course we don't want them to be fully powered, fully energized all the time. That would be that can actually help improve avionics. And I think even earlier than that, I was just like trying to understand, like, what are you designing any of these avionics components like in-house? Like are you guys designing it, or are they all like commercially off the shelf? Would be interested in knowing some design challenges and like key considerations that were being made for that.
Based on based on the our team members' availability and the future team members who may join, specifically in regards to electrical engineering related fields, we could definitely look into going in-house option of integrating all the components, the sensor chips directly into our our own embedded board. But we are right now going for off-the-shelf components that we could obtain because the development speed, as well as right now we don't have the expertise in being able to manufacture our own sort of circuit boards. And for temperature sensors, there is one temperature sensor on board the airspeed sensor. So it is bundled together. So the airspeed sensor compensates automatically based on the temperature. And I believe there is also one on board the flight controller as well. And for IMU choice, I do have a note here, just in case someone ever asked, I wanted to go over. So we did a bid, as mentioned before. We did a bid for IMU and GPS research. And based on that, and especially given the speed where our vehicle will be going at, for autonomous navigation, I wanted to ensure that we have state estimator conversions, as well as we could detect all the sampling aliasing from our dynamic mode frequencies on board. And based on that research, we ended up deciding on this specific unit because it was able to output at, I believe, 8,000 hertz data output rate, as well as 40 G plus minus dynamic range for accelerometer, and 13 micro G in run bias stability. So for phase 1 flight, this would be more than enough, but for phase 2 flight, we may have to reconsider our IMU choice.
Thank you for explaining that.
And I would love to get in touch with you and discuss further on these topics, because I definitely need more guidance in terms of these sort of specific components, as well as validating our choices. So
absolutely.
And briefly on SLS part, so I think the I did blur the line between what we're using for hardware in the loop simulation and software in the loop simulation. For pilot training, that's definitely going to be a hardware in the loop simulation, as well as integrating the real flight test data into our simulation. But we do have a pure software in the loop simulation where we are emulating flight controller software and all the sensor data in a computer without any flight controller hardware.
Yeah, would love to hear how you guys are doing that, just because that is what I do for all my rockets. So would love to hear more about that. And also, I think someone talked more about like the FAA, like in discussing like all the testing for that. Based on my experience for the projects I worked on, there are some, like FAA does require some level of testing on avionics. So I could definitely reach out to you and then kind of explain to you what that testing looks like. And yeah, but great job, you guys. Thank you for answering my questions and points. Looking forward to talking to you about this offline as well.
Awesome. Thank you so much. And just for everybody else attending this, if you want to get in contact with us at Project Boom, you can email me at Colin, COLIN, @theprojectboom.org. I'll facilitate all the communications, and I'll transfer you guys and get you in contact with all of the leads to start conversations there. And if you're just a student that's interested in joining, please reach out to me as well, because we're always looking for new members.
All right, and then I think I'll go with Daniel. Do you have any comments?
Sorry, can you guys hear me?
Yeah.
Yep.
Okay. Yeah. I also have to say this is a really, really fantastic presentation. Props to you guys. This is an awesome project, very inspiring. So great job there. Really, I had just a couple of basic questions. If you guys had a general timeline put together yet for when you guys want to lock down your design and kind of get iterating with your testing, and when the first one's going to get built by. So that's my first question. And my second question was if you guys have a test plan put together and manufacturing plan generated.
Yeah, so I'll touch on the first part. So for our timeline, recently. So we talked about the two-phase plan in the presentation, and that's actually a recent creation within the project. So aircraft number one, our high subsonic aircraft, is going to start manufacturing early next year, so January, and then we hope to fly by summer of next year. Taking everything we've learned from that aircraft through the manufacturing, even before we get off the ground, we'll learn a lot that'll be useful for the second aircraft. And then once we get it off the ground and begin flying it, we'll take all that data and information, transfer that into a second aircraft, which we'll design for about a 2-month period and then immediately go into manufacturing for that as well. And that will hopefully fly at the end of 2021, so December or early 2022 in January. And that's the flight plan for both of our aircraft. The 2021 flight is attempting the Guinness World Record, so that's the first aircraft. The current world record is 450 miles per hour. We will be attempting about 600 miles per hour on our first aircraft. And then moving forward on the second aircraft, we'll be attempting Mach 1. And then, can you reiterate the second question?
Yeah, but before that, I have one more follow-up that's part of that.
Yep.
It seems to me like this sort of phase 1 vehicle is a really awesome test bed. So I think it makes a lot of sense for you guys to basically cover it in sensors and try to understand as much as possible about how your structure is performing. So one suggestion I have is maybe to include some strain gauges in key areas where you guys expect to have high bending moments, just to see how the frame performs. And then my second question was what your guys' general manufacturing plan was. Where are you building it, and how are you sourcing all the materials?
Yeah, so the plan right now is to get it manufactured professionally. There are a couple of different companies around the United States that build small UAS vehicles. You literally just give them your designs and drawings, and they manufacture the vehicle for you. So we are looking to reach out to those companies specifically, and either look at them getting a sponsorship through one of those companies or raising money to pay for that kind of manufacturer, which I believe Cole can talk on this a little more a bit as well.
Right. Yeah. So as Colin alluded to, a big portion of it has to do with the, sort of the funding or sponsorship with as far as the specific manufacturing, because, we have access to dozens and dozens of university manufacturing facilities that, particularly Skyler has done composite layups for small UAS. So we sort of have that sort of option, but we're keeping it open to hopefully do more of a professionally made version. As far as the testing and the location and stuff like that, and overall the test plan, frankly, throughout the summer, it's been keep our head above water as we, go through this design process, and we try to take stock as often as possible. So we're still basically keeping with the original timeline as far as have sort of a aircraft concept by, basically this week. And then we're going to really try to move forward with iterating that further. So the structural design, for instance, isn't super far along. The actual placement of some of the components, stuff like that. So that's sort of where we are in the design thing. But yeah, we're really trying to sort of pick this design and go forward with it. And then as far as the propulsion system is sort of a different aspect of that. So we kind of expect that we can still break the speed record even with just the off-the-shelf FT250. And the reason we have confidence in that is it's basically just an upgraded version of the current world record holder engine. So it's not really a different world or anything like that. But we still want to mess around with getting as much thrust out of it as possible through an afterburner, just modifying the exhaust nozzle. There's been some work at OSU that we've seen increasing the thrust by 25% just from changing the nozzle, stuff like that. So that's sort of open-ended and a little bit difficult for us to put an exact timeline on, especially since we don't have, 40 hours a week employees to budget time towards. But having said that, we're kind of headquartered in Stillwater, Oklahoma, as far as the engine development part of it. just because we have a lot of people there and some facilities that we can access to actually do physical testing. But moving forward, we expect to probably have to throw the engine in some sort of high altitude, high speed environment to really get a better idea of how it's going to perform, particularly an afterburner. But yeah, we're currently working on detailing out the steps as far as what we need to prove. So as mentioned before, avionics and sort of maybe what the FAA would like to see as far as that goes. But in short, we'd be super open to advice as far as what makes sense as far as an order. We should have that pretty soon, and maybe we can communicate that with people and get some feedback.
Okay, excellent. Yeah, I think that was pretty much all the feedback I had. You guys are doing wonderful, so keep at it.
Awesome. Thank you so much.
Thank you, Daniel. And Dean?
Can you hear me?
Yeah.
Okay, great. Wonderful, guys. What a great presentation. Thank you so much. So you guys done some great work here in such a short time. It takes about 7 to 8 years on average to design an airplane in commercial space. So what you've done in this short amount of time, I really am impressed with. I wish I could get the people I work with to move that quickly. The world would be a much better place. So first of all, shout out to my man there in Manchester. It's like 1:52 in the morning right now for him. So thanks for staying up late with us. And I'm a structures guy, so I loved your pitch as well. So just a bit of a sub note. I'd like to understand on the whole team, like 100 people, I think you said, what the diversity is. I see a lot of male faces there. We really struggle with having a lot of women in the industry. And I'm sure there are women on your team. I'd just love to know how that compares to industry. If you got a higher percentage than we do in our industry, which is just a shame. So if you wouldn't mind, Colin, just let me know that. It's just I have an interest in that.
Yeah, I can comment on that. We actually have those statistics. If you're, we're about 17% female, which you compare that to industry, we're about 7 points higher. Industry usually sits around 10 to 11%. University can hover higher, up closer to 20%. So we're proud of that, and we're continuing to try to grow our diversity, specifically on that aspect. So.
No, that's great, and I think that's a real high marketing point for Shiva. That's excellent. Thanks for doing that, and I really appreciate it. That's the way we want to go, right?
And if I can touch on that a little bit, I think the goal going forward is to make sure that we're highlighting as many. And I know we talked about this in our channel the other day as well. That we would love to talk to some awesome female industry leaders on our podcast. And really grow that presence. I know one of the people I've worked very closely with is Allison Gundrum, and she has been doing a lot of work for us on marketing in that end. And we have so many great, I feel like we have a lot of potential to grow in that area as well. And I think this project in its brand and its core is made to be something that is inclusive of everybody. And that just begins with our project being a global project.
Yeah, no, totally agree with that. So thanks, that's cool. So I'll try and keep this as quickly as I can because there's others to speak. So I'm used to going through 3-day design reviews for one LRU, right? So in 2 hours, you cover the whole airplane. So it was a lot for me to take in. So I actually took notes on each section. I don't really want to go into the technical detail here, but I'd be more than happy to speak with you guys after the weekends, whatever you guys are free. I'm happy to give my time and donate that to you guys if it helps. Okay, so I'd like to know more. So in propulsion, the inlet that you showed looks a little small in my mind. I haven't done, obviously you can't see doing any analysis, but you have to be really careful with how accurate you manufacture the balance of that inlet, because any kind of offset there would cause some catastrophic stability issues, right? So just something to, I would say, consider. What I would suggest maybe considering as well is a baffle design. So it changes, it's mechanically changed with the speed of the airplane. So your baffle closes as the higher speed you get to stop that sonic boom damaging the blades. That's certainly something I think you'd like to consider. And what kind of fuel are you using in the engine?
So I can speak to that. So for the fuel, at least at the moment, we are planning on using diesel just because it's more readily available for us, and isn't vary too much from jet fuel that we've from our analysis that we found. And for the inlet, yeah, so for that image, that was like kind of a preliminary image of it. But yeah, we are looking heavily into mitigating supersonic or effects from shocks from going supersonic.
Gotcha. Okay. So with a diesel engine, you have to go for glow plugs. You go for some glow plugs trying to heat the engine, or
We haven't looked into that at the moment.
Right.
So we're still working
Okay.
on that.
Okay, I think maybe traditional fuel will be easier, especially with the temperatures. You're 17,000 feet, so you're probably about minus 20 degrees Celsius, about 3 degrees Fahrenheit ice a day. So I guess that was another question I had. What is the constraint on 17,000 feet? The higher you go, the easier thing, the more thrust you'll get, right?
That's a regulation requirement. After talking with the FAA, they strongly suggested we stay below 18,000 feet because that's where a lot of airline traffic, you start being regulated on that end. That's also going to depend on where we test, though. We didn't touch much on this during the presentation, but we are looking at testing in restricted airspace, so possibly at a U.S. military base or something like that. And we might have access to more airspace if that's the case. However, we're planning for the worst case scenario where we are limited to 17,000 feet.
Gotcha. I mean, to overcome your thrust concerns and your thrust issues, which you talk about very eloquently, go higher, man. Air thinner is much easier, right? So, okay. And I was thinking maybe the desert or somewhere, so unrestricted, or maybe even a different country where they would allow that to happen. So in terms of the aerodynamics, if you look at the thermal loads at Mach 1, it looks like you're going for composite design right now. So the thermal loads on the composite structure might be too high. That's something I wondered if you considered yes yet.
The thermal load on the compulsive, can you repeat that, I guess? Because honest to God, I probably haven't thought of it because you're hitting me like a deer in the headlights right now.
Oh, sorry, no, the thermal loads on the composite structure. So as you go faster, you're going like 700-800 miles an hour, you're going to burn up a lot of friction.
I personally haven't ran any thermal analysis on the skin heating, for example, the friction heating that we could expect. But some people within our group have told me that we're okay, and I trust them. So that's basically the best answer I can give you at this point, because I can't rattle off the numbers off the top of my head because I didn't do it. But
okay, no worries.
As far as like the skin that we choose, which is more kind of on structures and manufacturing, that we could basically anticipate, either carbon fiber or fiberglass as a skin structure material. And so beyond that, we're just kind of going as thin as we can get. We're talking about potentially doing a titanium nose cone, or
that'd be a good idea.
Very least aluminum for obviously, protection against the impact and also heating. And different things like that. We may have to deal with RF frequency loss because we're potentially going to have carbon fiber. So we need, a place to have our radio frequency delivered and vice versa. So that's the best answer I can give you, because that's as far as I've looked into it on my end, if that helps at all.
Yeah, sure. You fly plastic at high speeds through, you're going to generate friction, right, and static, and then you can screw your electronics. So yeah, definitely something kind of things to think about. But it sounds like you've got some people on the team who can take that into consideration. And then on aerodynamics, I just wondered if you considered using VGs, vortex generators on the wing to smooth the airflow. Something you may want to look at. Traditionally, you wouldn't think about in the supersonic aircraft, but something you might want to consider. Small ones, like minute size, less half a millimeter, maybe a 16th of an inch, 8th of an inch, something like that, that size of an airplane, just to kind of give you some laminar flow, boundary layer distraction kind of things. That's where they go. And then stability and control, you also can need very, very fine movements at high speed from your actuators. So it sounds like you've got an autonomous system, which is easier to do than I thought it was a handheld system initially. So glad to hear that. But yeah, that's something I'm sure you're considering as well. And then have you considered any of the sloshing effects in the fuel tank as well? So As you got all the fuel in the center there. As your fuel burns and as you go through faster, it will go quick, right? You're going to have a lot of sloshing. So any slight movement, you're going to have a big stability control there. So I think I'd consider look at baffles, maybe neoprene baffles in the fuel tank as a consideration.
Yeah, we're actually designing the fuel tank. We just started a few days ago, actually, as we nailed down the variant that we're going to go with in the power plant, the subsequent power plant for it. And so, yes, yeah, that is something that we've considered, talked about it a little bit, sloshing and reducing that. But we're to kind of put you where we are in Project Boom right now, or the need that we have. It's like we need as much CFD analysis as possible. And that's basically kind of one of those things that as we design different types of fuel tanks and things, we'll just run it in CFD to kind of give us an idea. And then obviously we'll do real testing from there if we get somewhere we like or we feel comfortable with this. But yeah, we're just kind of at this point now to speak on your vortex generation comment, because yeah, we've talked about that, especially for phase 1, where we're not going to go supersonic at all. We've definitely talked about looking at some vortex generators and stuff like that. So we're just kind of waiting on running everything through CFD a lot more to get to those iterative process or to those iterative points where we can make decisions like that. But yeah,
okay. Yeah, and I'll try and keep the last bit down to 1 minute because I know that other people want to talk, and I got so many questions, but I don't have time. So is it Gaurav, the structures guy? So write this down: continuous composites in Coeur d'Alene, Idaho. They're a groundbreaking technology to making out of mold composites, and might be a great way of designing your thing without the tooling and getting the tolerances you need. And they're also a young startup, so they might be willing to help as well. So
what's the name on that again?
Continuous composites. Just type in Coeur d'Alene, Idaho, and they'll come up. Great company, and they've got a lot of great videos on YouTube. They do a lot of TED Talks, so I think you'd really benefit from talking to them. I'd say look at testing, do DO160 testing. You don't know how your sensor are going to happen. I mean, those sensors you got for your autonomous system, what happens when it gets minus 20 degrees, right? Are they going to react quick enough? Are you going to be able to move your surfaces quick enough? So you got limited test vehicles. You don't want to crash them and ruin them and delay yourself and the costs. So I'd say do as much testing as you can. Do DO160 level testing, environmental testing. And then the airspeed sensor, I'm not too sure if you're looking at a NACA system or a PITO system, but certainly a NACA system would be better for your design, I think, with less drag. And again, I wouldn't go with a landing gear. I'd go with a launch system and a parachute, because the landing gear would have to retract. It's going to take up too much space. It's going to be too heavy, too complex. I wouldn't even consider. I mean, you're not flying people around, right, or cargo, so it doesn't really need to land on the runway. So I would go for a launcher and parachute. I think that'd be a better way to trade the cost. I got loads more, but let's talk after. Thanks very much, guys. You guys doing a great job.
Yes, sir. Thank you so much. And yeah, for everybody, if you'll write down all your questions, we can organize private conversations between all of our team leads to talk about all these things in a lot of detail.
Thank you very much, Dean. And Noah, I'm going to mute you if you have any comments.
Yeah, thanks. This was really great, guys. This is an awesome presentation and awesome work by everybody. I'll keep mine pretty short and sweet because we're, I think, a little bit over time here. My main question was about the performance modeling for the engine and afterburner. It seems like, at least for phase 2 flight, you're very dependent on reaching a higher thrust than what the engine is demonstrated to show right now. How are you going about buying down that risk through performance modeling?
I'll let Colin Mann take this one.
Yeah, I think what you're getting at is like kind of our, given that it's experimental, how do we account for those like margins in, you know, what we're expecting? Am I interpreting that right?
Yeah, sure. And also just performance of your afterburner in general and the design of that. How are you going about that?
Right. Yeah, so we're super duper preliminary on the afterburner stuff. So as far as the 50% thrust increase was what we sort of considered a sort of a nominal goal, more or less. I think just this week, we've had some calculations come out sort of updated for our aircraft concept what we actually expect our thrust increase to be. Unfortunately, I haven't been able to run over those yet. So yeah, that is the spooky thing, and is a big reason why we went to this phased approach where we don't necessarily need the afterburner for the first aircraft to still break the record. Is that we don't have a high degree of confidence right now in how much thrust we're going to get out of it, whether that's 10% or 100% or whatever. I know a major problem with these small engines is, one, they're too small to have like turbine blade cooling, so they're limited in that aspect, but they have really low pressure ratios. So we're probably not able to get choked flow in our engine, period, unless there's some creative ways around that. So that sort of gives us a limit as far as what our exhaust velocity could potentially be. So that's sort of the bounds that we've worked from. But again, we've just run some of those numbers this week, but I haven't looked over those personally. And again, yeah, we've allowed a lot of wiggle room in our mission analysis calculations. So like for the P400 variant, if we get a 50% increase in thrust, it looks like we'll be able to nudge right past Mach 1. But yeah, the margins are too slim for us to be like, okay, yep, let's do that and break the sound barrier. So that's definitely something we need to work more on.
Great, I appreciate the response.
Yeah, just to add on, yeah. So at the end, I kind of touched on like the test stand that we have. So we're designing it for the K70 as a proof of concept to see if it's even possible for us to get 50%. So if it's not, then it's just something we'll have to consider other options to increase our thrust, which our second option would be rocket augmentation, which we didn't really speak a lot about because it's our kind of like our backup plan. But yeah.
Cool. Yeah, thank you. And I guess the second question I had was like preliminary component selection. You talked about the electrical components, but how about hardware components for control flap actuation and stuff like that? What kind of work have you done into speccing those and factoring them into like your CG estimates and all those systems?
Maybe Skyler.
Yeah, so we haven't done too much selection. I've done a lot of preliminary look at what kind of actuators will work well. So one of the big reasons for this is we haven't decided how much actuation we want. And that's one of the biggest things, is looking at those forces that are going to happen during it. So we're waiting for some CFD analysis. And that's what I've done in the past when we picked them, is have to see what kind of torque we need on these. So the idea for the ones on the elevons is they'll almost be directly controlled. I really want as little of a moment arm between the servo and the actuation surface as possible, especially with how thin we want these wings. So we want to keep our servos off the wings in that case. So the CG of those is going to be pretty close to where the turbine is. And that has been included in a little bit of the calculations there. And then for the canard, that's going to be a little more complex of a system. The canard, we want to be able to rotate fully. And that's something I'll be working with Gaurav and structures on how we want to actually implement that in to be relatively smooth with the rest of the surfaces so that we're not having so much interference drag. So we want it to be as simplistic as possible. For the rudder, which would be the most complex of getting those to work, we would need the least force to actuate that. And one of the other complexities in the rudder is we don't really need one, except for maybe some purposes. So like AMA and some of the other companies require rudders on certain sized vehicles. But most of this scale, rudders are only used for on-ground control when turning from one direction to another, like on the tarmac. So it's not really necessary at this scale. So we're kind of neglecting that for now until we figure out that we really need one to be implemented. And due to the low control necessary, we can keep that relatively small. Elevon control, one of the other things I want to do to help mitigate flutter is I'm looking into systems right now that will be a lockout mechanism for those elevons. So that once we're about to get towards a transonic region, we can actually lock those structurally into place so that there won't be flutter effects across those elevon surfaces. So.
Cool, great answer. Thank you guys, and really good job. It's pretty inspiring what you guys are doing. So thanks for having me on here as a judge.
Thank you.
Thank you so much.
And thank you all. And I think, Ben, I'm going to mute you. You seem like you have a question.
Yes, hey guys, it's awesome what you guys are doing. Really good presentation. Of course, time is sort of a little bit short, so I'll get straight to it. Has there been any consideration about airspace constraints for the mission profiles? Like, for example, where are you planning to fly? How high can you fly? How far away you can fly? What are your turning assumptions when you need to return back to speed tracks? Essentially, how much room have you sort of given you guys to sort of maneuver in with the accessible airspace options that you have on the table? And how has the team taken this into account to make informed design decisions to date?
So I'll start and then I'll hand it off to more of the engineering side. So part of it has to do, like we said, this is a lot with where we're going to test. We hope to test at a location like White Sands Missile Range, where there's a couple of large military Air Force bases in Oklahoma. If we were able to test at one of these locations, we would have a very large restricted airspace where we wouldn't have to worry much about wandering out of this. However, one of the smaller locations we would test at has it's about 3 miles by 3 miles square. So we'd have to stay within that boundary. And I'll let Skyler and them talk about turning radius and kind of those kind of things. And
oh yeah, this is one of the things I've been working with Gaurav very slowly. We haven't had any direct implementation of this yet, just because a 3 mile square is relatively small for an aircraft that's attempting to go 600 plus miles an hour. At that case, you get very, very little time to react and turn. So you're going to need large actuation surfaces, which are very difficult to structurally maintain, especially at those speeds. So it's not really feasible. So we're looking at some of our larger locations like White Sands and some of the others that have miles and miles of just open airspace that you can go, where we can just instead do a large dive or rise in order to burn off some of our extra velocity and then slowly glide to a better safe location. For either, one of the things we have talked about quite a bit is a parachute landing. So if we're able to burn off enough velocity to do that, but one of the issues with a parachute is it takes up a large volume. We'll need like a 15-foot diameter parachute for our aircraft weight in order for it to fall at a safe velocity. So there's a lot of things that are in place with that question that make it a little more difficult to give a direct answer to. So I apologize for the "it depends" kind of situation on that, but we are taking our size that we can fly into a large comparison for a lot of our constraints.
Yeah, because I've tried to sort of personally design this as well here in New Zealand, and one of the biggest problems that I've got is there's, of course, as you guys mentioned, the sort of restricted airspace. There's not a lot of size in there, and I think probably it might be worth actually having your first design probably go for a more conservative approach. So actually design something where it actually can fit within those parameters, or even your second to smallest sort of case size. Because then if you do get sort of access to larger airspace, then you basically covered all the bases, and then it just means things can sort of still progress. And I think I would probably recommend that doing that first, just in case your options don't really sort of open up. And I think that's quite important because that will affect everything in the design. And I think that needs to be quite an important consideration even before sort of moving forward. So
One good thing about our aircraft is that if we do have to bleed any airspeed, our acceleration is pretty crazy because of our thrust to weight ratio. And so basically it comes down to like a mission profile, a range thing. Is the more we slow down, the more we have to burn fuel to speed back up. And so, yeah, you're exactly right. I'm hoping and holding out for a larger than a 9 square mile test bed. But I think that we have talked about it and looked at it enough to say that we are considering the option B that basically you're saying. And I think that a lot of our loading factors and stuff that Gaurav and Skyler are looking at are basically assuming that we can still maneuver this aircraft, well above 100 miles an hour. So it's not like we have to get to our stall speed to start a maneuver, basically. So, but yeah, you're right. Mitigating any chance of not being able to complete our mission or even try it before we get to that point is a great idea.
I just wanted to jump in to give a tiny point as well in addition to this. So from the structure side, for example, we have, like I showed in one of the slides, we have written a program to essentially calculate the VN diagram. So for example, as soon as we start to get some more precise values from aeros, things like the lift curve slope and CL max, things like that, we can essentially nail down the load factors, and from there we can sort of calculate what kinds of turns we can take and reiterate that into aero and work on the design. So that's just a bit of a thing that we, at least from the structure side, has been doing to take this particular thing into account.
Yeah, so I think probably what will probably be quite useful to know moving forward is probably doing some sort of crude simulation or whatever, just to sort of at least give an idea what is sort of possible, really, because I think that will just help make things a little bit more streamlined, sort of moving forward. But yes.
I was just going to say, you took the words out of my mouth. I was going to say that our avionics man, Minos, is working on and pretty much already has a version that works, but is working on getting a simulation that flies the entire flight path for us, because it's going to be an autonomous flight controller anyway. So that way we can sit back and watch on screen, what theoretically may or may not happen. And if nothing else, it'll give us basically, an amount of time that we're in the air, speed changes, acceleration needs, things like that, so we can get a more calculated or an exact fuel burn and stuff. But I think I interrupted you. Apologies.
No, I appreciate it, and I do have other questions, but I recognize that other people want to answer some questions, so I'll leave those sort of privately. But otherwise, thank you for answering my questions, and I hope that sort of provides sort of some more clear guidance in terms of sort of moving forward, because of course this thing it's not easy to do, and we're all sort of willing to sort of share our knowledge to help with the sport, because it's an exciting thing, especially during these sort of uncertain and sort of anxious times. And happy to be a part of this.
Awesome. Well, thank you so much. Yeah, please reach out to go over those in detail.
Cool. Awesome.
Yeah, I think
anybody else?
To respect everyone's time, I think we can take one more question. If someone has a question, they can raise their hand. And
Awesome. Well, if it looks like nobody else is gonna ask any questions, if you think of any more or want to get in contact or help, please reach out to my email. I posted that in the chat, but it's colin@theprojectboom.org. You can also find us at www.theprojectboom.org. Thank you, everybody. Thank you, Aldo, and thank you, AIAA, for hosting us. This has been an amazing event for us to get us our work out there. And we can't wait to see where this goes in the future.
well, all right, then I think we'll wrap this up. And like I said, definitely reach out to them. I think this is a very new and innovative approach to trying to beat the sound barrier. So again, I'm glad that you guys took the time to spend and hear us out. And then if there's more questions, definitely the websites and the contact information has been put in the chat.
Thanks, everybody. Bye.
Yep, thank you.
Glad to see a lot of our members in here.
Yeah, it's awesome. Yeah, thank you so much, everybody. Good job to everybody on the project. We'll go ahead and get off here and let everybody get out. Thank you again, Aldo and Ken, for hosting us.
Oh, great pleasure. Anytime. So next time, welcome back again. The more, the better. So it's good to see your great progresses. Yeah, this is amazing. Really amazing. You're all, fantastic.
Thank you. And then Aldo will be in touch.
Listen, all right, guys, have a good night or good morning, depending on where you are. All right.
Yep. And then,
Thank you, Aldo.
All the leads, let's transition to Team Lead Zoom.
Thank you, Aldo.
Thank you.
Thank you, Aldo.